Good morning. Welcome to all that have joined us today for this webinar. Today we will present several demos on how the Sodalite framework helps to improve software application development and deployment. To put these demos in context, let's just recall the general structure of the Sodalite framework. In the figure on the screen, coming in on the left, we have a model of the application. Coming in on the right, we have a model of the various infrastructure that are available. These are fed into the Sodalite IDE, Integrated Development Environment, which produces a deployment plan and application components to run on the various infrastructure. The application is then deployed on the infrastructure according to the deployment plan. During runtime, the application and the infrastructure are monitored. If needed, a change is made to the deployment plan, and the application is then redeployed. We will be demonstrating the following Sodalite features. First, how to build an abstract model of an application. Then, the image builder, followed by deployment adaptation, and finally, elastic resource management. The first demo is how to build the application deployment models. Yosu.
So the idea of the demo is to showcase how can we create abstract application models when we are adopting the role of experts, but then we introduce the entirely the options that are offered by, the features that are offered by the Sodalite in supporting the modeling of different models. So we are supporting the application of experts in modeling abstract application deployment models that are targeting cloud or HPC infrastructures, where we are also supporting resource experts in modeling reusable and shareable resource models that are stored within a common and shareable repository that we are using, that is a semantic knowledge base. And all these things are supported in the IDE, in the Integrated Development Environment. We can, apart from creating these models, we can also deploy these models into the knowledge base, and we can also deploy the abstract application models into the AIC Sodalite subsystem. So concerning the authoring of ADN, abstract application deployment models, we are supporting textual modeling for fast model creation with context-sensitive assistance, which is enhanced by the knowledge base reasoning capabilities. But also we are providing visual representation of these models for communication purposes. In case of the other models, for instance, resource models, we are focusing on textual editing with the same similar features for modern aids. So in the demo, I will focus on the creation of an abstract application deployment model. I will create a new job for an HPC application that can be deployed within a HPC workflow manager. And I will showcase different context assistant capabilities provided by the IDE, supported by the knowledge base reasoning capabilities. So I will go to the IDE. This is the IDE, which is based on Eclipse. In this IDE, I have opened an existing abstract application deployment model. There are different views, different editors. One is the textual editor, this panel. Then we have a visual representation of the same model, which is in sync with the textual editor, textual model. Here we have a model explorer with all the models I have in my workspace. And also I can have an outline, which is based, it depends on what is the model I am selecting, that is tree-based for the textual model, or is an outline, visual outline for the graphical representation. These two models are in sync, so every time I introduce changes in the model, they are reflected into the visual representation. The visual representation at the moment can be edited through the properties file when I am selecting, for instance, a particular job, a particular application component in my visual representation. I can also modify some aspects. And in the future releases, we will provide a complete palette for creating the model also from the visual editor. At the moment, we have to create the models by using the textual editor. In the textual editor, we are at any time supported by content assistance. So that is providing me hints to complete model entities depending on the point of typing. The context assistant is different. It could be describing me what are the grammar entities that are expected at that point. So for instance, here, when I am describing a particular component, I can provide different features for this component. And for instance, when I select one, I am retrieving from the knowledge base what are the existing types this component could be of. This information retrieved from the knowledge base. And also, for instance, in case I am writing prop attributes, I am retrieving from the knowledge base which are the attributes that are or has been associated to this type, and I have a description of each attribute, so I can select the one I want to override. So, as an example, I will create a new job. So here I have to provide a job ID. I will provide job 5. And then I have to provide a type. There are different features I can provide. One is a type. And here I can select a type from the knowledge base, one of the existing ones. And in this particular case, it will be a job. And as soon as I save the model, I get the new entity visualized in the ID, in the visual representation. So here, for instance, I can override some properties. I will provide a name. So it's suggesting me the concrete type for this property. So that will be job 5 name. And also, for instance, I can also provide a script template. That will be my job 5. Similarly, I can provide, for instance, requirements. The job has to be deployed in a particular job workflow manager. So I will satisfy the requirement, the host requirement. This host requirement. Oops. Yes, I have to select a node. And the only node that is available at the moment is this HPC workflow manager Torque. So that will be the one I will select. And when I update my model, when I save my model, I see the new host requirement that is being satisfied by Torque. I mean, I see this dependency described by the host requirement between the job file and the Torque. Similarly, I can create a dependency. Here I can select a node. Oops. And this node I will select HPC Torque 1. And then when I save the model, I have a new dependency from job 5 to the job 1. So before the job 5 is being executed, it's executed after the first job is being executed. So here, I mean, every change in the textual model is reflected in the visual representation. But also, I can also modify here some aspects. I could select the different types, or if I select here the dependency, I can select the job. And if I change this one, the dependency change. So I can also edit partially the visual model through the properties files. Well, once that I have the model complete, I can also use the Sodalite menu, the store menu, in order to save the model into the knowledge base. I can also deploy the model into the ISC infrastructure. And there will be other features that will be implemented, like, for instance, to get optimization recommendation and other features that are being implemented at the moment. And that's concluding my demo. You can have more information about this ID in this GitHub repository. Thanks for attending.
Thank you, Yosu.
I will start sharing.
The next demo is on the image builder. Dragon will present.
Okay, hopefully you can hear me now. So I'll try to share my screen. Okay, maybe you can see my screen now. So now we are talking about a different part of the Sodalite platform. This part is about the deployment pipeline. So actually, in this picture, we see an overview of the Sodalite general architecture with the three layers. And at this point, we are talking about the infrastructure as a code layer, which is also concerned with deployment of the preparation of deployment blueprint. So actually, in this second image on the right, we see where the image builder comes into place in this deployment preparation pipeline. It actually takes the definition of the application and then builds the images for the private registry for now. So for this part, we built a component with the REST API. It's actually accessible through our GitHub. This is the GitHub that we are talking about. So it's about the REST API that encapsulates the framework for building the images for a private registry for now. We are also targeting possibly to change this to for the images to be accessible also on the Docker Hub, private and public access. But for now, we have only a private registry pushes to of the images. So basically, what the implementation is all about, we prepared a REST API and encapsulated the orchestrator in this REST API, so that we can use Tosca workflows for building the images. The great thing about this is that we can use the same Tosca in any other workflow for doing this. So actually, we encapsulate the REST API to be accessible from anywhere in the platform or from outside of the platform. So to enable the users to define the images, the Docker files that they want to build, and to push these Docker files to be reusable by the other components in the deployment pipeline. Okay, now for a short demonstration. So this is how the Sodalite image builder REST API looks like. It's protected by HTTPS. We have a standard user operation to prepare the users to access this REST API. First, we have, of course, to log in. I just happen to have the login prepared, so I'll just log in here. All is done through the JSON. To the Swagger JSON, so you can actually very easily test the components we prepared. After logging in, I got success here, and actually with the bear token, which is a JWT token, I can authorize myself here. This part will also can be changed with any JWT token implementation. We plan to use Kicklock for integration of all the components later on. So basically, now we can test if we have the access to the building part. We see success here. So actually, we can try and use the builder component for building this for building the images. I'll just copy the part I want to test here. Second there. So this is the JSON definition of the part we want, of the component we want to publish on an internal Docker registry. You see the definition of the sources here and the build context, which is done through from the Git repository. We define the source URL, which is a Docker file here, and actually supply the passwords and things like this. Through the HTTPS, it's safe. And we define the target image. For now, as I said, we define only the private registry part. So this image will be called Daily Median Aggregator. It's one of our use cases implementation. And we'll try to execute this building of the image. We got the response. So we successfully submitted the Docker image for the building job. We also get this session token. The session token is used to check how the building process is going on. So actually, there is another path for testing this. We can use it here because the building process can take some time. This is the way we can test this. Of course, we fail here because there is the job didn't finish yet. But we can use another endpoint to test if the image is building. So you see here that the image is in the state of building. It should be quite soon done, hopefully. Meanwhile, let me present how the definition of the Tosca is done. So this is the part where we define the Tosca workflow for building these images. So as you see, we have the source part, which defines from which components we want to build. These are usually Docker files. These are tokens that require GitLab or GitHub access. And this is the building context when we download the code, and later on we define the targets in here. The targets are actually do the push to the internal Docker registry. So let's go back to see if the image builder did something. Okay, at this point we got done. So actually, we built the images from this example and pushed it as this name to the internal private registry. And these images can then be used, as you also showed before, in the deployment process. So they can be targeted in the definition, in the modeling process of the preparation of the blueprint. I guess this is all I had to show. I'll be ready for the questions. So this is the way we access the Image Builder REST API. We have all the definitions and the usage of the Image Builder REST API on our GitHub. So please check and let us know if you need something else here. Thank you, Kalman. This is all from me now.
Okay, thank you, Dragon.
I'll stop sharing.
Okay. The next demo is on deployment adaptation. Indica, please.
Yeah, I'm sharing my screen. Can you see my screen?
Yes, go ahead.
Okay. So I have actually video. So in this case, refactoring part. So there's a two demos. So the first refactoring is based on knowledge-based refactoring. So I will first introduce briefly design of this refactor. So we have a infrastructure, and then we have application deployed on the infrastructure. Then orchestrator manage this deployment. Then we have a semantic knowledge base that have uh, all knowledge about this application and infrastructure, which include not just about the current application, but also possible alternatives, like possible alternative component, possible alternative resources and constraint, and so on. Then this event-based refactorer, so it listen to the event from the system. For example, application can directly publish event. Then the refactorer based on event. So event indicate the situation that need a resolution in terms of new deployment option or new deployment model. To find the new deployment model, refactorer use the knowledge base. So the knowledge base include all the knowledge about possible alternatives. So we have a refactoring option discoverer that can suggest new possible deployment option. Based on this option, refactorer calculate a new deployment model and send this deployment model to the orchestrator. And then orchestrator deploy the new deployment model by calculating difference between current model and the new model. Then orchestrator can gracefully redeploy the application. So in this specific video, so we are demonstrating within the context of Sodalite vehicle IoT use case. In this use case, in this scenario, so vehicle move from Germany to Austria, and that means the location change. So when the location change, so the compliance of the application, for example, with respect to GDPR, is violated. So in order to resolve that, in order to prevent that violation, we need to redeploy some part of the application. So in that case, so when the location change, we need to come up with a new deployment model that match with the constraints imposed by that location, and deploy that new deployment model. Here, so we have three part showing here. One is the refactor the component. It's a RESTful provide the RESTful API. There's a client and the orchestrator API. So there's no application, so we can deploy the application first. Using a refactorer, we can send the event to the refactorer, asking to deploy application. So yeah, let's deploy the first one. It support location Germany and Austria. So now this one send the event. Based on the event, then there's a knowledge base, then there's a rule. So is a event condition action rules. So based on the event, then this within the rule logic, it use semantic that deployment option discoverer to find the new deployment, and then use the orchestrator API to enact the found deployment. These are sample the rule used in this case study. You have an event and then the action. So the refactorer use orchestrator to do the deployment. So we can see or check the progress of deployment using the orchestrator API. So because its deployment takes some time. Here you will notice that the virtual machine is created, so it's a deployment in progress. Oh, now there's a response from the application for the location Germany, and So that means application already has deployed successfully. Also for the Austria. Now we going to show the refactoring part. So now there's no server for the location Italy. So when the client make a request with Italy, then the application asks from the refactorer to deploy a new deployment model that has a server in Italy. So this one return an error message. If we are in this case we use Italy. So it return an error message because service not available in Italy, but it also trigger redeployment. So this event application send this event, refactor receive the event and trigger a rule. So we can check that redeployment status again using the orchestrate API. So it's still deployment in progress, but after some time, after a few seconds, it so it's a deployment is complete. So redeployment is complete. So we can actually now get the response from Italy. So that means new deployment model is inactive. So we now so that's all about the this part of the refactoring. Any questions? So yeah, after the end of all the demos, we can actually if we can, I can answer any question you have after the end of the all demos. So the
Okay. Thank you,
okay.
Indica. The next demo will be on the Elastic Resource Management. Giovanni, please.
Yeah. Can you see my screen?
I believe so.
Yeah. Okay.
Yes,
Stop
we can.
me if you don't. Okay. So I'm Giovanni Quattrocchi from Politecnico di Milano, and I'm going to talk about Elastic Resource Management. So as context, the target of this demo are machine learning applications in inference mode. And we are selecting these kind of applications because they can exploit heterogeneous resources. In particular, they can be easily executed both on CPUs and GPUs. We are targeting inference mode, and in this case, applications are interactive and they are low latency, meaning that they can be executed, each request can be executed in milliseconds. And in this context, the service level agreement, the SLA, are defined by using requirements on the response time. So for example, you can say that an application must have a response time less than half a second. So the challenges in this context are, I would say, many. So first, we have to schedule requests for execution on the best optimized device. It could be a CPU or a GPU. Also, we have to optimize the resource allocation in order to improve its efficiency and not waste money. Of course, we have to self-adapt the application because we need to meet the requirements. So we don't want violations. And currently, if we look at the tools that we can use to run these kind of applications, in particular Kubernetes and TensorFlow. TensorFlow is a well-known software for running machine learning application, both in training and inference mode. Well, these tools lack the support for SLA, so they don't support natively SLA. So you run your application, they do some kind of optimization, but they don't support this kind of requirements. So our solution basically wants to use efficiently the heterogeneous hardware that is available by exploiting orchestration tools. In fact, our solution is built on top of both Kubernetes and TensorFlow. And we use dispatching policy in order to select the best device for each resource, for each request. And also we keep the response time in control by, of course, monitoring some metrics for each app running, and we fine granularly allocate resources in order to meet the SLAs. Well, we have two main enablers for our solutions. First, containers. So container is a lightweight virtualization technique. And in particular for our solution, containers are important because they are very fast to boot. They are very fast to scale. They can be scaled even vertically, which can be done in hundreds of milliseconds. We can scale containers at a very fine-grained granularity. And they provide isolation through different running application on the same machine. And in fact, our solution controls multiple applications running on the same cluster of machines. And there are well-known orchestration, as we have already talked about, of containers, in particular Kubernetes. The second enabler is control theory, which is, let's say, the logic that we use to carry out the resource allocation. And control theory provide automatic means for controlling a system. In our case, once again, machine learning application in inference mode. And we use PID controllers for providing the resource allocation. And we use this kind of control because it's very lightweight. So since containers are very fast to scale, we needed a very lightweight technique for providing the resource allocation, and PID controllers are quite fast to compute the next allocation. It can be computed in constant time. And of course, control theory provides some design time guarantees. So this is the architecture of the solution, and also using the architecture, I will introduce the experiment that I'm going to show. So say that we have two applications. In particular, for the experiment, we are using GoogleNet and Skyline Extractor. So GoogleNet is a well-known deep learning application provided by Google, of course. And Skyline Extractor is an application provided by one of the Sodalite partners. And so these applications have different workloads, of course, because they are completely independent. And they are deployed on a cluster of virtual machines. In this case, we have a quite simple cluster with two virtual machines running on the Azure cloud. And these machines have 6 core each and one GPU each. So the solution, and as you can see, each application is deployed on both the machine. And they are deployed by using TensorFlow in containers. So TensorFlow provides the runtime for executing the machine learning part. So the solution is divided by two components. At the centralized level, we have a dispatcher that basically optimizes the scheduling of requests. And I'm not going into the details, but we use two different policies for dispatching the requests. For GPU for GPUs, we use a custom heuristic based on the longest queue algorithm. And for CPUs, we use a simpler round-robin policy. And for CPUs, we use a simpler policy because at the distributedly, we have PID controllers deployed on each machine. And in particular, we have one PID controller for each application deployed. So in this case, we will have two PID controllers for each machine, one for GoogleNet and one for Skyline Extractor. So let me run the experiment. I'm going to show you 4 charts in parallel. So the first one is about response time. So here we will see how response time changes during time. The step is set to 1 second. So each step that you see, each point in time is 1 second. And the GoogleNet response time will be shown in red and the Skyline extraction in green. And these horizontal lines in green and red are the SLAs set for the 2 applications. So we don't want the response time to be higher than those lines. Then we have the workload, which is defined by showing the number of requests incoming per second. Also here we have the number of requests executed on the GPU for the 2 applications, keeping the same color as before, so red for GoogleNet and green for Skyline extraction. And this is important because, of course, GPUs are faster than CPUs. So when an application has a higher workload, it should be preferred. The execution of its request should be preferred on the GPUs and not CPUs in general, of course. And here we have the core allocation. So at the beginning, we will see a quite constant core allocation at 1 core. And then when needed, CPUs will be used for avoiding SLAs violations. So let me start the experiment. So at the beginning, we have a, I would say, moderate workload for the 2 applications, around 20 requests each, and the response time is more or less constant. Of course, we have some fluctuations which are corrected by some additional cores and allocated, and also not completely constant allocation on the GPUs. So here, as you can see, we have a peak on the workload of GoogleNet, the red application. And so we basically the number of requests are free per with respect at the beginning. So it's 60, before it was 20. And as soon as we have a peak, of course, we have an increase in the response time because our approach is reactive. But as soon as we have the peak, we increase the number of GPUs requests allocated and also the cores. And as you can see, after we have the response time, which is always below the SLA requirement. And the same goes for the Skyline extraction. In fact, after the peak of GoogleNet, we have a peak here for Skyline. And basically, it works the same. So as soon as we have the peak, the allocations, both of CPUs and GPUs for this application is increased, and the response time is kept under control. Of course, we have some fluctuation, but you have to remember that these each point is 1 second. So if you aggregate over a larger time window, basically we have 0 violations for both the applications. And then the workload returns to the moderate type, and basically we have the response time under control, the number of requests on GPUs more or less normal, I would say, and more or less a flat core allocation for both the applications. So that was the experiment. Thank you, and I'm waiting for questions if you have.
Thank you, Giovanni. Okay, so we have a few moments for questions. Maria, if you could unmute, please, the participants, if anybody would like to ask a question on any of the topics, any of the demos, or on Sodalite in general.
I think that they are able to unmute themselves if they want to ask something.
Okay. If there are no questions, then I want to thank everybody for participating in this webinar. Additional information about Sodalite can be found on the project site at sodalite.eu. You can write to us, ask us questions, and we'll try to respond. And then this concludes the webinar. Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.